Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. Earlier, we reported that China has become the second nation ever to land a mission on Mars. Their rover, Zhurong, has landed in Utopia Planitia. Following in the tradition of tourists everywhere, Zhurong has taken a selfie and photographed its Instagram worthy surroundings. According to a post in Nature, the exact landing site hasn't yet been imaged by HiRISE, but similar regions show remarkable dunes. With the constantly changing surface, there is the potential for Mars to reveal its past like so many fossils revealed in a changing desert.
We use the techniques we've learned on Earth to understand our world to now understand Mars. But this isn't to say we actually understand Earth. One particularly terrifying event in 1700, for instance, is now getting new attention. On January 26, 1700, an earthquake killed the population of large swaths of Vancouver Island and the surroundings, and also sent a tsunami sweeping across the ocean all the way to Japan, where it was still able to do damage. This was triggered by a slip in the Cascadia fault line. Concern that this fault line could once again trigger an earthquake around magnitude 9 influences building construction in the northwest of the United States and Canada, and is part of the justification for earthquake and tsunami alert systems. These systems, however, assume all the damage was triggered by a single quake. Now, researchers modeling the damage spoken of in oral histories of the First Nations people in that region and marked in the geological record are considering the possibility that this event wasn't just one horrifying earthquake, but may actually have been a series of strong earthquakes over several days and years. According to study author Diego Melgar, the tradition has been only a megaquake explains everything, and what I found is that's not true. A megaquake still can explain everything, but so can a sequence of events. This is decidedly not good news. While a single massive magnitude 9 or so earthquake is horrifying, a series of magnitude 8 earthquakes would continue to damage and re-damage the region, making rebuilding efforts perhaps feel futile during the decade of devastation. To understand which of these two scenarios, a megaquake or a series of massive quakes, matches reality, detailed study of the coastal rocks are needed. It is well understood that the coastline changed as a result of the quake or quakes, with the coastline subsiding or dropping as the fault line shifted. If the shift occurred all at once, the record of small organisms living on the rocks will show a sudden change along the length of the coast, while a series of quakes and piecemeal subsidence would cause the organisms on the rocks to change over time. Either way, I'm fascinated, and Pamela continues to refuse to move to Vancouver.
I do admit to being really worried about that fault line. When the Cascadia Fault slipped, ocean water was sloshed into the mountains, where it created saltwater marshes and killed trees. While I love the science of this, I choose to live where there are tornadoes instead of tsunami. We all have our limits. Maybe. I mean, physics doesn't always seem to have limits to how large or small some phenomena can be. Pulsars, to switch topics wildly. It turns out that these tiny dead stars can spin at all manner of speeds, and using the fairly new and truly giant Fast Radio Telescope in China, scientists are starting to document these extremes. In a new paper in Astronomy and Astrophysics, researchers released the first findings of the galactic plane pulsar snapshot. With 5% of the survey complete, they've already found 201 pulsars, including some of the lowest energy pulsars so far detected. They've also found 16 binary systems. While pulsars are interesting for their own qualities, they are more massive than the sun, the diameter of Manhattan, and can spin thousands of times a second. Pulsars are weird enough on their own to be worth studying. But they are also a useful tool for looking at the properties of our galaxy. As their pulses travel through space, they are dispersed by the particles scattered about. Pulsar pulses are particularly sensitive to the distribution of rogue electrons. These early results seem to indicate that there are a lot more electrons than previously understood floating between the stars. Over time, as this survey grows, we'll be able to map out this distribution and understand how it affects our view of the universe beyond. After the break, we'll look at how we map our world and how it is sometimes as hard as mapping the universe.
As much as we struggle to understand the depths of outer space, we are still struggling to map our own planet. Getting to the seafloor requires us to build vessels capable of surviving extreme pressure, coldness, and making their measurements in utter darkness. In some ways, designing for the vacuum of space is far easier, actually. And if a spacecraft springs a leak, it can probably be repaired with a space version of duct tape. That doesn't work with high pressure water. This is where we find, working parallel to space explorers, a company of aquanauts who work to define what lies beneath the seas. In a new study answering one simple question, where are the deepest points in each ocean? This proved far more difficult than thought. The Five Deeps expedition has published new depth data in the Geoscience Data Journal and documented that while the 10,924 meter deep Mariana Trench remains the deepest point in all the oceans, other deep spots aren't quite where we expected. For instance, we'd thought there was a particularly deep trench off the coast of Java, and there is. It just happens that the lowest section of the trench is nearly 400 kilometers away from where we'd thought. Ingloriously named Unnamed Deep, and we thought astronomers were bad, this trench descends to 7,187 meters. In the Southern Ocean, along the trench spanning from South America toward Antarctica, there is also a newly discovered spot named Factorian Deep that lies at 7,432 meters down. This is a reminder that the oceans are far more vast than the land. Mount Everest reaches up to only 8,849 meters, and the deepest parts of the ocean are more than 10,000 meters down. Now, instead of asking, why do we climb? We need to start asking, why do we descend?
Understanding the history of our world requires researchers of all disciplines to work together to try and build as true an account of the past as we can. Humans are notorious for telling the stories they want to be true. We also can sometimes lose information in the passing of stories from generation to generation. We understand the Cascadia Fault in part thanks to the histories of the First Nations people and the efforts of researchers to record these stories before they are lost. This is a relatively straightforward process where geology, oral history, and archaeology in both the Cascades and Japan all tell the same story of an earthquake and a massive tsunami. Other stories are harder to sort and feel easier to dismiss. For instance, in the 6th century, there was a sudden pattern of water miracles recorded in Italian texts, such as dialogues on the miracles of the Italian fathers. While miracles aren't where one would normally go looking for evidence of environmental change, in this case, these stories pointed to a sudden societal interest in water-related issues. Working together, historians and geologists were able to determine there was a temporary and dramatic change in rainfall that led to myriad water-related disasters of varying size. To understand this, you have to look at things from a political perspective. If you are in a place where the people are afraid of flooding rivers and other water-related crises, you want them to believe their government can protect them. Today, this would lead to politicians discussing plans to build new levees and drainage systems. In the 6th century, it instead meant politicians discussing how powerful individuals had performed water-related miracles to save the lives of communities. Just as we can't always trust politicians to follow through and build levees, we also can't trust historical leaders to have always spoken of true miracles. There may have been real lives saved in some instances, but all we know for fact is the uptick in reported miracles reflected a region in crisis as too much rain led to environmental damage. So scientists, it turns out, we need to know history to understand our Earth, and historians, you need to know science to contextualize our history. After the break, we'll be back to discuss weird and unexpected chemistry that tells the history of our solar system. It's not just the history of our own planet that we continue to try and understand. It's the history of our solar system. And one of the ways we try to understand our solar system is by studying asteroids and comets, those smaller bodies that formed in the very young solar system about 4.6 billion years ago. In a new study published in Nature, scientists have taken a look at the atmospheres of about 20 comets to try and understand these icy bodies. Yes, comets have atmospheres. In fact, a separate team studying interstellar comet 2I Borisov found nickel vapor in its atmosphere. And this team found both iron and nickel vapor in the atmospheres of their 20 comets. These results were surprising all around because while the metals are expected in the interiors of the comets, they weren't expected in the atmospheres. Heavy metals don't become gaseous at low temperatures. Even more strange, the two metals were found in equal amounts in these atmospheres when normally there is 10 times more iron than nickel. So why was there iron and nickel vapor in the atmospheres of comets some 480 million kilometers away from the sun? That's the new question being asked. Co-author Emmanuel Jayan notes, comets formed around 4.6 billion years ago in the very young solar system and haven't changed since that time. In that sense, they're like fossils for astronomers. These results mean we still don't completely understand our early solar system, but co-author Damien Houtzemakers explains, we came to the conclusion iron and nickel might come from a special kind of material on the surface of the comet nucleus, sublimating at a rather low temperature and releasing iron and nickel in about the same proportions. More work still needs to be done, and we'll update you as we learn more.
If you want to get even heavier elements, like gold, uranium, and plutonium, you need a really violent event to happen, like two neutron stars merging. Or so we thought. Now, though, a new study published in Science examines the possibility that it merely takes a supernova to produce such elements. Maybe. The story starts with the discovery of an extraterrestrial isotope here on Earth in the ocean crust, plutonium-244. This isotope was found alongside another radioactive one, iron-60. Both of these isotopes are evidence of something violent happening close-ish to our solar system millions of years ago. And then the interstellar gas and dust that contained all these radioactive elements lingered and found its way to Earth. We know they weren't part of the material that formed our solar system because these elements would have completely decayed in the past 4 billion years. So why do these scientists think that a simple supernova, if a supernova could ever be thought of as simple, created the plutonium-244? Because it was found alongside that iron isotope. We know that iron-60 is formed in supernovae, and for the plutonium to be coexisting in the crust, they may have formed together in a supernova that happened near Earth. Yikes. Lead author Anton Wallner notes, however, our data could be the first evidence that supernovae do indeed produce plutonium-244, or perhaps it was already in the interstellar medium before the supernova went off, and it was pushed across the solar system together with the supernova ejecta. It's an interesting line of research, and I'm curious to see where it goes. Either way, it continues to come back to the fact that, as Carl Sagan said, we are all made of star stuff. We'll be back in just a moment to talk about the upcoming total lunar eclipse in our weekly What's Up segment. Stay tuned. When we look at the night sky, we are seeing the history of all that has been and the conditions that will define all that will be. You just need to know where to look. One of my favorite pieces of science learned as a child is that a killer asteroid killed the dinosaurs while spreading a layer of iridium over the planet and creating weird features, cenotes, in the Yucatan Peninsula that allowed civilizations to thrive geologic epics later. On any given night, you can go out and easily photograph asteroids moving across the sky if you just have a way to track your camera or a telescope with a camera. Tracking means your camera changes its position to move with the stars across the sky. Since asteroids move faster, you can see them as jumping dots moving between images in a series. The best place to look for these wandering stars is along that band across the sky called the ecliptic. This band is both where the sun can be seen and where the planets move in their orbit, and it represents the disk of our pretty flat solar system. This line is making itself easy to find right now. Looking west at dusk, you can see the line of Venus, Mercury, and Mars, with the moon rising fairly high in the sky. As the night progresses, the worlds will sink, and to the east, Saturn and Jupiter will rise, rising up to define the eastern path of this band. Software like Sky Safari can help you identify these worlds. It uses your phone's sensors to tell you what is in the sky behind your device as you look around. Go out, look up, look at our solar system, and know that you now know roughly what part of the sky hides a potential dinosaur-killing rock. All of that geometry leads to a pair of special events that occur during what we call eclipse season. Season is a bit of a misnomer. It's not a season like spring or summer. It's a period of time when we get a pair of eclipses, one lunar and one solar eclipse. Now, these eclipses aren't always or even usually total eclipses. They don't block out the moon or sun completely every time, and every pair of events is different. But this next pair happens to have a total lunar eclipse, which makes it exciting. This total lunar eclipse will happen on May 26th, and it will be a short one. Totality, that period when the moon is completely covered by the Earth's shadow, will last just over 14 minutes. We get a bit of a bonus here because it's also the closest full moon of 2021, making it a supermoon. According to Earth Sky, this total lunar eclipse is visible from western North America, southern and far western South America, the Pacific Ocean, New Zealand, Australia, and Southeast Asia. From the Americas, you'll want to be up early in the morning before sunrise. From the Eastern Hemisphere, you'll want to go out at sunset. The moon will either be setting or rising respectively, and then you can watch it move into and out of Earth's shadow, turning red during totality. Unlike a solar eclipse, you don't need any special gear to watch a lunar eclipse, so get out and take some pictures. We'll have all the exact times and charts on our website at dailyspace.org. But what about if you're not in a region that will see the total eclipse? Well, the good news is that if you're in the rest of the Americas or the eastern half of Asia, you'll get a partial umbral eclipse where Earth's shadow will take a bite out of the moon. Sorry, Africa and Europe, the geometry doesn't work out for you this time. You will, however, get the opportunity to view next month's annular solar eclipse on June 10th. We'll talk more about that event when we get closer. For now, though, this has been the Daily Space. You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.